laboratory scale. Okay, this meeting is now being recorded. He's going to be talking about laboratory scale testing of formed catalyst particles. Chris, over to you.
Thank you very much, Chris. Can people see my screen?
Yes.
And the slides?
Yeah.
Excellent, good. Thank you very much. And thanks for the opportunity for talking today. As the title says, what I'm actually going to talk about, as I say, is some particular aspects of laboratory scale testing of catalysts. And so I move on to the introductory slide, and hopefully that's moving for everybody. So I'm just going to talk very briefly about why testing of formed catalyst particles is important, and then talk about how you might approach that in the laboratory. And then actually the bulk of my talk, what I'm actually going to talk about is a test methodology using what's called a single pellet string reactor. And I'm going to give a bit of a review of literature on that, and then give a specific example as well that we've used ourselves in SABIC recently. And then I'll have a conclusion slide at the end. So that'll take me about 20 minutes, I hope. So if I move on. So why is it important for us to test catalysts? It's because it's in industrial catalytic processes, many processes used fixed bed reactors. We're talking about either a packed bed, sort of like might be an adiabatic bed, or a tubular reactor where the catalyst is packed in tubes, which might be sort of 2 to 5 centimeters in diameter, internal diameter, and the catalyst is packed into those tubes. And the reasons we use fixed bed reactors is quite often because you're worried about, in a full-scale process, pressure drop over the reactor, so you can't use a fine powder in a large-scale process because you have excessive pressure drop. And you also need to worry about things like heat and mass transfer in such reactor systems. And as well, for many catalyst systems as well, when you come to use them commercially, particularly those based on precious metals, because you have sort of mass transfer limitations, you would tend to use eggshell catalysts, so where the active phase is distributed towards the outside edge of the catalyst particle. And in that case, what you can't do is test those catalysts as as powders. You have to test them in the full-size particle shape. So, you know, when you're scaling up a process, you know, actually the production of that formed catalyst is a necessary step in terms of the manufacture of the catalyst. And therefore, you actually need to be able to look at the performance of the full-scale catalyst in some sort of test arrangement in order to be able to design the full-scale reactor and process. So that's one aspect why you need to do that. And although there are models people use to extrapolate the performance of sort of powder catalysts to sort of full-size catalyst particles, you're probably better in many cases to look at actually the performance of the full-size particle rather than having to use the models to do that. And the other point you might do, even for an existing catalyst process, you might want to be able to compare the performance of a commercially available catalysts, i.e. what we call a sort of a benchmarking exercise. And again, you need to be able to test the full-size catalyst particles, particularly if they're an eggshell material. Just as a picture there, you know, and the problem about when you come to test catalysts, they can be of a variety of different sizes and shapes. So on the left-hand side there, you can see a simply pelleted material, but for some applications, you might use much more complicated shapes of catalysts. And this is why it becomes important to test the full-size particles. So here on the right-hand side, you see an example of a steam reforming catalyst, where you've actually got quite a complex particle shape. And this is why it's important to be able to evaluate full-size catalyst particles. When you come to test catalysts, conventionally people would say, but testing of full-size catalyst particles is more challenging because the increased scale of the test, because of the particle sizes can be much bigger. You have to worry about sort of safety aspects of the testing you do because of the increased scale. And typically you would also need increased flow rates of reactants and things like that. So as you go to testing more and more catalysts, you need increased reactor flow rates, and that has implications for what you can do in the laboratory. Quite often people talk about a rule of thumb for fixed bed reactors, and they say therefore that the the ratio of the tube diameter to the particle diameter needs to be at least a factor of 10, and the length of the bed versus the particle diameter needs to be greater than 50. When you take these rules of thumbs, when you now test a full-size catalyst particle, that tends to imply much bigger reactors, longer reactors, larger diameter, which creates some problems in terms of how you do that test in the laboratory. One thing that people talk about using is use what they call basket reactors as one option. So, for example, a Berti reactor or a Carby reactor, here where you place your catalyst pellets in some sort of spinning basket or a fixed basket with an impeller, where you're trying to simulate the performance of a stirred tank reactor. However, these types of reactors are actually a lot more expensive to purchase and also quite complex to operate, and you need a lot of experience to be able to use those successfully. Typically, what people talk about when you're trying to test formed catalysts in the laboratory, they use a technique which we call bed dilution. And quite often people use silicon carbide powder for that. And the reason for doing that is effectively you decouple the hydrodynamics of the reaction, hydrodynamics from the reaction. So there, the hydrodynamics are the flow behavior in the reactor is determined by the small particles, for example, the silicon carbide particles you would use. And that effectively becomes the relevant reactor to particle diameter ratio. You tend to have longer beds because you're diluting the catalyst. You get better heat conduction, so heat removal, or if you've got an exothermic reaction because you have something like silicon carbide present, you have a larger heat transfer area, and therefore you get a less heat produced per unit volume. And the way that might look like, you can imagine here's a schematic of how the particles might be packed inside the diluent material. So you've got in the blue, you've got the catalyst particles surrounded by a smaller diameter silicon carbide material, for example. And in practice, I can show that does work. However, there are problems, and there are references here of how you can do that, just to show you. And the literature you can look at for this, it's been studied quite a lot in the literature, and these methodologies are used quite successfully in industry. One of the problems is, here's an example of how we might do this. So here you see a reactor tube, a glass reactor tube in this case, being packed with full-size catalyst particles, sort of almost layer by layer in this case, surrounding by silicon carbide particles. So you can see that quite clearly how you might do this in a reactor tube. One of the problems from doing this, however, it has limitations. If you have a lot of dilution, it can affect the conversion you achieve. You need to make sure that you do achieve a uniform reactor loading from one experiment to another, so you can get variability in the packing when you do this, and you still require larger equipment in sort of terms of the reactor dimensions and therefore also feed flow rates and things like that. So these can be a challenge. What I'm going to try and talk about instead is a different methodology called a single pellet string reactor. And I think the name is fairly explanatory, but I'll illustrate some examples in a few minutes. The first thing to say is these things are not new. They've actually been used originally for the determination of transport properties in porous pellets, for example, sort of effective diffusivity of gases within the particles. And sort of these methodologies were developed sort of back in the early to mid 1960s, and people first started to apply these. However, they have also been used for different reaction studies over the last 40 years or so. So actually, the first reference actually came across is actually with Haldor Topsoe, and back in the early 1980s, they talked about doing ammonia synthesis in this sort of in a pellet string reactor on full-size catalyst pellets. Whereas probably, I think it was 1983, that first reference. But there's a whole pile of different chemistries people have looked at over the last 40 years. So for example, sort of methane dry reforming, dehydrogenations, various liquid phase reactions, N2O decomposition, vinyl acetate monomer synthesis, acetylene hydrogenation, and even hydrodesulfurization. So a wide variety of different chemistries have been looked at in the literature over the last 40 years. There's about 30 to 40 different literature references of people doing this sort of different chemistries using pellet string reactors. So I'm going to give you a couple of examples from literature here. So the first one is actually from work that was done between the University of Delft and also the Avantium company a few years ago. And here they looked at the hydrodesulfurization in a liquid phase reactor, so really trickle flow with a nickel molybdenum quadrilobe catalyst. So effectively they looked at a model reaction looking at the hydrodesulfurization. And what they did is did a comparison of sort of catalyst pellets or extrudates in sort of small scale reactors, which are only 2 millimeter diameter and about 30 centimeters in length, the total bed. And this shows schematically how they did these sorts of experiments. So they did this in a high throughput experimental facility. So they were able to do many reactions in parallel. And then made a comparison of the results in that sort of experiment versus a conventional packed bed, which is this point is sort of 700 millimeters in length and 20 millimeters in diameter. And they compared the results in the two different setups. And some of the results are shown here, which is showing on the sulfur in the final product coming out of the reactor, comparing the bench scale reactor, which is the data in blue, versus the single pellet string reactor in green, and at some different process conditions, different temperatures and different space velocities. And what I should point out is on the vertical axis, the scale is a logarithmic scale. So actually they've got quite good comparative data between the two different setups. So basically they're saying is in their work, they say, I can do the work either in a sort of packed bed, which might have had sort of a couple of 100 grams of catalyst in it, versus an experiment in a pellet string reactor where you might have only had sort of 3 or 4 grams of catalyst. So you can imagine on a single pellet string reactor, it's a much smaller scale, but you can get comparative data of a relatively small number of catalyst particles compared to a conventional packed bed. The other bit of literature I want to refer people to is some work that's been carried out by a consortium called Eurokin, which is a European consortium of industrial partners who have an interest in sort of reaction kinetics and testing. So they've done some work with an academic group, and there's a reference at the bottom of the page here. So they did some work where they did a sort of a modeling study using computational fluid dynamics of a pellet string reactor set up with a model reaction. And then just showing here, there's a picture from that. And initially they did work with spherical materials. And what you can see on the left, on the side here, is sort of the setup with 20 particles packed in a narrow diameter reactor. And they set the system up with a model reaction where they assumed that in a conventional plug flow reactor, you would get 80% conversion. And then they were going to look at how the performance of the pellet string reactor deviates from plug flow behavior. As I say, they did CFD modeling, so they could look at, for example, here, sort of velocity profiles through the bed. And what you can see from the way the picture looks here is effectively the flow moves around the particles as it descends through the reactor. And there's a zoom in here, so you can see the velocity profiles around the particles. What they then did is actually said looking at an 80% conversion system, they looked at the conversion you would achieve as a function of the length of the reactor, depending on the number of particles that are in the reactor. So they looked at a reactor with just 5 particles in it, 10, 20, 50, and even 100 particles, and tried to compare the performance of that versus a plug flow reactor. So again, it's pictures of the velocity profiles that they obtained there. And as you can see, so in a 5 pellet reactor is clearly shorter than a 10 pellet and versus a 20 pellet. So effectively they're changing they're keeping the contact sign the same to give the same conversion, but the velocity is changing in each experiment. So notice you can see here, for example, at 5 particles, clearly we're getting a lower conversion than with 10 versus 20, for example. So one of the things they worked out from their studies, and you can see it in the data here, they get some back mixing carrying on. So actually, and the very first particle gives you a higher conversion, and the end of the bed gives lower conversion. But otherwise, the conversion per particle in the middle of the reactor is effectively constant. What they looked at is the deviation from plug flow. So a plug flow reactor gave us 80% conversion, and you can see the deviation as you increase the number of pellets, the deviation from plug flow decreases. So at 20 pellets, the conversion you're achieving is only down by 4% relatively, which is actually a pretty good performance, because in a laboratory reactor, normally you're trying to achieve something which is performance is within about 5% of plug flow behavior. So it suggests that that's sort of quite a reasonable approach. What they then did is take that data and try to convert it into some sort of design criteria for an experiment where you take into effect sort of the gas flow rate you're using and the geometry of the reactor, and look at the deviation from plug flow as a function of the Peclet number in the reactor. So this is about the flow behavior in the system and the number of particles. And they came up with some design criteria for that, for the deviation from plug flow. So that's quite an interesting study, and they've actually extended that study since this initial publication to look at sort of extrudates and things as well, not just spherical particles, and also if you've got exothermic reactions present and things like that. So that's quite an interesting study. Okay, I'm going to move on now and talk about an example from within SABIC. And the example I'm going to use is actually looking at methanol synthesis as an example. And I think most people know about what the methanol synthesis, but I'll give a quick introduction to methanol synthesis as well. So yeah, methanol synthesis, people describe this as a reaction of a CO and CO2 with hydrogen to produce methanol. And you also have a water gas shift reaction as well, of CO with water. I think most people are probably aware is that sort of in industrial conditions, over the copper, zinc, alumina catalysts which are used in industrial processes, the source of the carbon for the methanol synthesis is from the CO2. So it's really the CO2 and plus hydrogen reaction and the water gas shift reaction are the two important reactions here. Typical industrial conditions between 200 and 270 degrees centigrade and between 50 and 100 bar pressure. Just for the sake of interest, this is actually the first plant that was built in the world using what was called the ICI low pressure methanol synthesis using these copper zinc catalysts. And this is a picture of a plant in the northeast of England in Billingham from 1966. And actually this is a picture of one of SABIC's plants today, which makes something of the order of 1.6 million tons of methanol per year production. So significantly bigger scale. And actually what you can see here, if I look at the picture, this is the reactor in the original ICI process for the methanol synthesis. And these here is the reactors in the current day process. So in terms of how they physically look, they look quite similar in many ways. So in terms of the experiments I've been doing, we've been using a commercial 6mm by 5mm cylindrical pellets. That's 6mm diameter, 5mm in height. And we've packed that into an 8mm diameter reactor with an inert spherical sphere between each pellet. And what I've looked at is testing reactors packed with 5, 10, 15, and 20 catalyst pellets in parallel, using a syngas composition, which is typical of an industrial process. And we looked at a range of temperatures at 70 bar pressure, and also a varying contact time by varying the gas flow rate as well. So how this actually looks in the reactor, this is a sort of a mock-up of a reactor tube, and here what you can see is the individual pellets. There's 10 pellets in this case, separated by an inert sphere, and this is held inside the sort of the reactor furnace. So the pellets are sort of, say, 6 millimeter diameter in an 8 millimeter diameter reactor. I'll come to show you the data, some of the data again. This is quite a complex slide, but I'll talk people through it. So effectively, I'm comparing 5, 10, and 15 and 20 pellets over a period of an experiment which is lasting about 400 hours. And the red line is temperature, so I've increased up to 220 and stepping the temperature up and down to 250 or 270. And I'm varying the flow rate through the reactor systems, which is the blue line. So I'm going up and down in flow rate through the reactor as well. So what you can see, if I start at the first end, what you see is the methanol formation rate. As I increase the number of pellets, the methanol formation rate increases. If I increase the gas flow rate, the flow rate increases a bit. And you can look at all these changes. But what you can see under some conditions, the methanol flow rates for the different reactors close up. And the reason for that is, if I go on to the next slide, rather than looking at methanol formation, looking at the conversion of the carbon monoxide, in this case, and what you see, for example, at the first set of data, the carbon monoxide conversion increases, but it starts to approach the equilibrium conversion. So again, at the lowest flow rate, for example, here, there's 5 pellets, 10 pellets, but 15 and 20 pellets almost give the same result. If I increase the temperature to 250 degrees, you can see there's 5 pellets. The other 10, 15, and 20 pellets give almost the same conversion. Doesn't quite get to equilibrium, but they're pretty close. So what we can look at here is try and understand what that means in terms of reaction kinetics and the number of pellets we have. If I take that CO conversion data and plot all that data in a different way, well, now I've actually sort of scaled the number of pellets versus the flow versus the conversion you get good trends of data increasing up to a maximum, and the maximum value they approach is close to the equilibrium conversion. So at 220 degrees centigrade, I actually expect the equilibrium conversion to be about 92 to 93%. So it's just below that. At 250 degrees, the equilibrium conversion is just below 80%. And at 270 degrees, the equilibrium conversion is just over 60%. So actually we approach equilibrium conversion as we increase the number of pellets in the reactor. Well, this shows how we can look at methanol synthesis quite successfully with a pellet string reactor. And I'll go and show you on the final technical slide I'm going to show you now, is actually where we can use those data now and decide on a set of test conditions to compare different catalysts. So all this data I've shown you so far is with a specific individual catalyst. But now I can look at some experiments where I can compare the performance of different commercially available catalysts. So here we are, I'm just plotting out on this graph here on the x-axis, the amount of methanol produced per gram of catalyst per hour. So grams of methanol per gram of catalyst per hour. And what you see for these 3 different catalysts, they have a different initial activities, but also you can see actually, for example, how the sort of the purple and the blue lines close up. They have different deactivation rates as well over a period of about 3 weeks here in these experiments. So we can use the pellet string reactor to do a benchmarking of commercially available catalysts, at least within methanol synthesis, quite successfully, and get valuable data where we can look at performance differences of these commercial catalysts. In summary, I just want to say, we have to be able to test formed catalyst particles, whether it's for catalyst process development and scale up or catalyst benchmarking in the example I've just given you. And yeah, you can use bed dilution and basket reactors, but I wanted to emphasize the point that this pellet string reactor concept is also a very useful approach. It's not something that is used widely, but I think it has a lot of merit. So that's all I wanted to say. So thank you very much.
I'm on mute. Thank you very much indeed, Chris. That was very interesting. In terms of questions, I don't see any questions in the chat. Corinne, do you have any questions that have been sent to you directly?
I haven't received any yet, but yes, please just
put
your questions in the chat.
Chris? Ah, here we are.
Any
one from
questions
Mysterious.
now?
Yeah, one from Mysterious. Are there any external mass transfer resistances, and how does one account for them?
Well, in the example I've given in the methanol synthesis, yes, absolutely there are mass transfer resistances. And actually what I'm therefore looking at is looking at the effective performance of the catalyst accounting for that mass transfer resistance. And that's why I prefer to do the tests on the full size particle rather than taking the material and crushing and sieving it.
Okay.
So yes, exactly. So the whole purpose of being able to test the full size particle is I want to take account of the mass transfer resistances in what I think the performance of the catalyst would be related to a full scale process. So yeah.
Okay. One from Nikolai. Could you possibly comment on heat transfer? The larger scale reactor is much more challenging. Does it mean the small scale reactor provides the best case results?
In terms of wanting for isothermal behavior, yes, but even with small scale reactors, it can be challenging to get remove the heat particularly for an exothermic reaction, particularly if you go up above about a reactor diameter above a few millimeters in diameter. Mm-hmm. So even when you're testing powder catalysts, you need to use a quite narrow diameters if you have a problem with heat transfer. I have some experiments from my own experience many years ago in with my previous employer. With a 4 millimeter internal diameter reactor, we managed to get an exotherm of 200 degrees centigrade on the powder catalyst inside the reactor.
Yes. Excellent. Nice thermal runaway there.
Actually, we could model the data quite well, actually. Chris.
As serious as Clarence said, he wants to clarify that it was external mass transfer, not internal mass transfer.
Yeah, so in the pellet, the one advantage of the pellet string reactor is because the way it's set up, you tend to have much higher linear velocities relative to the catalyst. So actually, you tend not to have external mass transfer limitations. It tends to be internal. You're dominated by. Okay. When you've got low gas velocities, that's when you tend to have problems with external mass transfer.
Right. Okay.
So actually, with the pellet string reactor, is advantageous in that sense because effectively you get high gas velocities, basically because the particles are close to the wall. So there's only small gaps for the gas to move through.
Okay. Two quick ones, I hope, and then we'll have to stop and move on to the next speaker. One from Adri. The design of the catalyst or shape is also important. How important is this factor to avoid the problems you mentioned?
It can be important, and actually, yeah. So in some processes, in the full size process, the shape is optimized because everything is dominated by some of the mass transfer effects. So it actually that's why, for example, in that picture on the very first slide, where you have for steam reforming, for example, where you even have holes inside the particles through the particle as well, to maximize sort of geometric area becomes important. So yes, it is optimizing the particle shape in terms of for commercial use is very important. Absolutely.
Okay, and we'll just have one more. What would the What would the dimensions of the reactor for testing methanol synthesis? The testing of the methanol synthesis catalyst.
So in the experiments I showed you here, I used an 8 millimeter internal diameter reactor. For the pellet, when I say they're 6 millimeter, they're actually fractionally over 6 millimeter, about 6.2 millimeter. So you can't really load them into a 6 millimeter diameter reactor. Ideally, the experiment would probably be best being done with something, a reactor diameter of about 7 millimeters would have been probably optimum. But you have to make some compromises sometime in terms of what's practically available.
Sure. Okay, I think that's all we'll go for, because we need to move on. But there is a question from Donato in the chat, Chris. I don't know whether you could type an answer to that rather than verbally do that. While
I'll look at that in a minute.
All right, that's great.
Thank you
very much indeed. We'll give you we'll give you a clap. Thank you very much indeed. So we're going to move on to Rob now. So Rob, do you want to start sharing your screen?
Sure. Okay. Can you see that okay?
Not at the minute. Are you using two screens?
Nope.
Okay.
So I just click on this green share screen button at the bottom right?
Yeah, and it should bring up a window, and you click on the slide that you need to share, or the program that you need to share. Yep, that's it.
I've got it. Okay. And then I go to full screen, I guess.
You go to full screen. That should be it.
How's that?
Great, thank you.
Okay.
So just over to Rob. He's going to talk about the challenges for the use and handling of powdered catalysts. So over to you, Rob. Thanks very much.
Yeah, thanks, Chris. So this is kind of a counterpoint to Chris's presentation. This is more about slurry phase reactions and powdered catalysts. So I'll get a little bit into catalyst selection and catalyst choice. So my name's Rob Parry. I've been on the Applied Catalysis Group committee for, I don't know, 10 or 12 years now, I suppose. I was formerly employed by Engelhard, an American catalyst company in the 1980s, all that time ago, which was bought by BASF in 2006, and I retired from BASF in 2018, and I'm doing a little bit of consulting and some online training and some of this kind of stuff from time to time as well. So that's a little bit of background about myself. So we're going to talk about pretty basic chemical catalyst reactions here. Many of the catalysts that you come across and you experience in your chemical reactions are formed catalysts, like Chris mentioned, but there is a whole world of nickel powders, even copper chromites and precious metal powder catalysts. I'm going to show you a little bit about catalyst manufacture, some of the materials that are used, look at the influence of mixing, just touch a little bit on filtration, because unlike what Chris was talking about, where you have a fixed bed reactor, there's no catalyst separation issue there. You just unload by vacuuming or by gravity when you change the catalyst. And I've picked out just a couple of commercial examples looking at the difference, for example, between Rainy type nickel, sponge nickel, and the ruthenium catalyst in a pretty simple reaction manufacturing sorbitol. I'll talk a little bit about deactivation mechanisms from palladium catalysts using an example of aniline, and then hopefully we'll have a little bit of time for some questions at the end. So just a few general slides here to show you where powdered catalysts might be used. So I mentioned sorbitol. In the fine chemical and pharmaceutical industry, when I started selling catalysts back in the 1980s, the pharmaceutical industry was using hundreds of tons a year of precious metal and nickel catalysts as well for manufacturing pharmaceuticals, and they were made in rather large chemical plants. The pharmaceutical industry has changed a lot and makes its drugs in quite a different way these days. There are still some drugs that use these kind of chemical, multi-stage chemical synthesis manufacturers, but the flavor and fragrance industry is another good example of where powder catalysts might be used, and of course oleochemicals as well. So again, a motherhood and apple pie. about creating chemistry for a sustainable future. What is driving catalyst demand and growth? Things like air quality, process efficiency, and energy efficiency. And I'll really touch more on the second two, which is process and energy efficiency using powdered catalysts. Well, not to insult your intelligence, but those of you who work with catalysts will recognize that the first row transition elements and these platinum group metals here are our main workhorses for catalytic metals. Over in this side of the periodic table, we use the oxides of silica and of aluminium, and carbon itself, the element carbon. And in this part of the periodic table, we find some of the more nasty materials like arsenic and phosphorus and sulfur, for example, that give us a headache in the catalytic world as catalyst poisons. So a very simple diagram to show you how you might manufacture a catalyst powder. In this case, I've chosen a precious metal salt. This could easily be a base metal salt. So you slurry this up in some kind of stirred tank reactor here, and you can make the catalyst in two different ways, usually by impregnation or by a co-precipitation. But what you want to achieve by this is, of course, good metal dispersion on the surface of the catalyst, so we get a nice active catalyst. You can also adjust the particle size, and that's a trade-off, it's a compromise. You don't want all big lumps of catalyst, and you don't want tiny particles of catalyst either, otherwise the separation and filtration is difficult. So we're always looking at a trade-off of particle size to get a nice active catalyst and something which will filter and separate easily as well. And when we talk about packaging and shipment, generally powdered catalysts are shipped water wet. Why? Because it's a safety issue. If you're shipping dry powders around with finely divided active metal, then you're going to have a pyrophoricity, you're going to have a fire problem. So usually catalysts are shipped as 50% water wet, particularly the precious metal catalysts. So thinking about mixing, and if we look at blending, suspension, heat transfer, and gas dispersion, I'm not going to read through all of this table, but with blending, we're talking about good homogenization to get all your reactants and dissolved hydrogen, if we're looking at hydrogenation, well mixed. With suspension, we're looking at good liquid catalyst mass transfer. With heat transfer inside your stirred vessel, you want to have a good constant reaction temperature. And then again, gas dispersion, if we're talking about hydrogenation or even oxidation, we want to make sure that our gas, liquid, and solid material, the catalyst in this case, are well mixed. So Chris really concentrated on this part of the reactor design, fixed bed reactors. He did also mention a multi-tubular reactor. We're interested in these kind of reactors for powder catalysts. So this is a continuous stirred tank reactor. You can see it's fairly basic design here. They can get a little bit more sophisticated with heating jackets and cooling mediums and all that kind of thing. If we're going to a more sophisticated design, then the Swiss designed bus loop reactor, where we get much better heat transfer, much better catalyst contact with the reactant liquids, and generally in a bus loop reactor you use about 1/3 of the catalyst that you would use in this continuous stirred tank reactor. This company in Italy, Biazzi, developed, well, I don't want to say a cheaper version, but let's say a surprisingly affordable version of the bus loop reactor. And nothing wrong with Biazzi reactors at all. They're very popular and very well designed, but they're not in the same league in terms of pricing as bus loop reactors. Somewhere else where powdered catalysts are used, of course, which I'm not going to talk about today, but is in an FCC unit, fluid catalytic cracking catalyst, where you're moving around very large quantities, hundreds of tons of powdered catalyst. So what about the influence of mixing on catalyst process and performance? Well, reaction rate is, as we've heard limited by the gas-liquid mass transfer. So mixing tasks generally are no limitation in most cases if we get good blending, good catalyst suspension, and good heat transfer. So let's have a look at an example of industrial hydrogenation. And actually, the equipment that is used is very similar to what I showed you in slide 6, how you manufacture a catalyst. The differences are quite often you have a catalyst makeup pot. Not always, but what a catalyst makeup pot lets you do is slurry the catalyst with a little bit of feed. Usually you're using a solvent in this. You can also put a little bit of hydrogen on there as well, and then you can introduce the catalyst into the reactor. Now in this reactor, you'll see that we've got what we call a hydrogen sparger. So you can introduce the hydrogen sometimes down a hollow stirrer, but in this case, this is a sparging device that helps with much better gas interaction with the catalyst and the reactants. So once the catalyst has done its job and you've finished your reaction, you can filter off the catalyst, usually through a primary filter like this. Sometimes the catalyst is sent back and used again. In the pharmaceutical industry, not. Why not? Because the FDA doesn't have any idea about what byproducts might be contained or trapped inside the catalyst. So in the more kind of petrochemical, fine chemical applications, that's where catalyst might be reused and sent back for a second, third, or sometimes it can be used 50, and I've seen catalyst used 100 times with a little bit of fresh catalyst added to help. And usually downstream from the primary filter, you would have an inline cartridge filter to trap the submicron particles, so you're not losing very valuable precious metal. If you're using something like rhodium or platinum or palladium, then you can trap out the fine material as well. So in hydrogenation, aromatics hydrogenation, double bonds, oxoalcohols is more of a fixed bed than a slurry application, but there's the one I'm going to look at. Sorbitol, selective hydrogenations are again a very popular use of catalysts in the hydrogenation world. So Chris alluded to this again in his presentation, and here is the issue of mixing and mass transfer and trying to get gas, liquid, and solid material all together in intimate contact so you get a good reaction. And here's what happens to your hydrogen concentration as the hydrogen tries to get inside the catalyst particle. With good mixing, you even see quite a large drop off. With poor mixing, you're going to have a problem. So it is very important to measure the mixing and optimize the mixing inside a hydrogenation reactor. So here is a chart to show you observed reaction rate, and you'll notice that the line of the reaction rate does not go through the origin, because in almost every reaction that takes place, and yet unless you're using ultra pure materials, and in my experience nothing is ultra pure, there is always some kind of poison. So when you add the catalyst, there will be this kind of lag period here represented by the red line, what we call the poisoning threshold, where you will get a lag before the reaction rate picks up. So that's a lab hydrogenation. You'll see that you get beautiful ideal conditions because you've got perfect mixing in the lab. When you get this out on the plant and you get less than ideal mixing, then that's the kind of reaction rate that you might see. I mean, I've cartooned the situation to show you that that there can be quite a difference between lab, and usually is quite a difference between lab and plant reactions. So a little bit about selectivity. What is selectivity? It's the ability of a catalyst to direct a chemical reaction to yield specific products and exclude others. We have a few handles to change and monitor both selectivity and reaction rate. So hydrogen pressure, temperature, how much catalyst you're adding, and how good your stirring is. And in addition, you get the opportunity to choose different catalysts. So in a low surface area catalyst, again, a rather a simplistic diagram, but I think it shows you quite well that in this case, we've got 30 square meters per gram, large metal particles, and this would have pretty low resistance against catalyst poisons. So what we're looking for is something like this, where we have a much higher metal area, which hopefully is going to give us much better activity and again, better resistance against poisoning, which will reduce that lag period during our hydrogenation process so that we can go straight on with our reaction. So what are some of the reasons during a chemical reaction that you might get particle size reduction? What you get is chemical degradation of the catalyst. There's friction going to occur between catalyst particles. Usually there are some pumps involved in your hardware, and generally I would use a diaphragm pump. If you get the chance and you're building a new plant, always choose a diaphragm pump, because this will reduce the shear forces on the catalyst over a centrifugal pump. And it is rare, but occasionally you do get poor quality support material, which starts to fall apart rather quickly inside the reactor, but that's rather rare. Okay, now what I was saying about friction between catalyst particles, if you take a look at a Malvern laser size distribution here, you'll see the perfect powder here, where you've got very small amounts of large material and very small amounts of the finer material. So what we've got here is a modified size distribution so that we have a very sharp peak here, rather than this kind of volcano curve where you've got a lot more of the larger particles and some of these problematic small particles as well. So a little bit about filtration. What are the targets and challenges of separating a powder from a reaction mixture after the reaction is complete? Well, you're trying to get a clear filtrate without any catalyst particles in it. Obviously, you want a high recovery rate for your spent catalyst. You want it to be safe and reliable. You want to get the maximum product yield, and you want to be able to wash off the catalyst and purge the reactor and then run another batch of your product. So here's some of the filtration technology that's available today, and I always regard filtration as the equivalent of printing when you're operating a computer. You can operate a computer, you can operate your iPad, but if you want to print something off, then that's a completely different world. Oh no, my printer's broken, and it's completely separate from your computer. And it's the same with filtration. Filtration is a completely different world to catalytic hydrogenation. And there are many customers that I've been to that have had wonderful hydrogenation reactions, but have bought either cheap or are running old filtration equipment. So filtration is just as important as the catalytic hydrogenation or catalytic oxidation itself. So here's some of the recovery systems, and what you're trying to achieve is a nice clear filtrate with very low percentage of solids. Here's some of the filtration companies, no favorites here. I've just listed 4 of them, but there are many good filtration companies around these days. And here's how a hydrogenation process might work, where we have our reactor here. We take the feed tank after the reaction is finished and run the mixture through. In this case, it's a candle filter, and then you might recycle a catalyst if it's not a pharmaceutical process with some fresh catalyst addition back for a second, third, fifth, 10th batch, and keep the catalyst recycling. So again, here's the factors influencing filter performance. Particle size distribution I've mentioned, particle softness, concentration, pH plays a role, the thickness of the cake, etc. So here's a candle filter. What does a candle filter look like? Well, the filter elements are vertical, and here's the filtrate outlet. If we have a look at a closer look at an individual candle, you can see how you can run this back pressure to discharge the catalyst cake, and it's all these days fully automated. So here's a pressure plate filter, for example. This, instead of having vertical filter elements, has got horizontal filter elements. There's a cutaway diagram of a plate filter, and then you can see the cake is discharged this time by vibration rather than by flushing off with a back pressure. So I'll skip over that. Let's just have a look at catalyst performance and look at a couple of examples before we close out. So let's assume that we found a suitable catalyst by our laboratory tests, and we want to optimize the amount of catalyst used, and we want to extend the lifetime of the catalyst as well by controlling poisoning, sintering, pore blocking, metal loss, etc. Typically, hydrogenation catalysts will be something like nickel, or cobalt, or palladium, or copper, or platinum. And I'm going to talk to you about this so-called rainy sponge type, and I'm going to talk to you a little bit about metal on a carrier as well, and how we can compare and contrast those. So in a rainy type catalyst, these are still quite commonly used in slurry phase hydrogenation. The great thing about rainy type catalysts is they're very easy to separate. You can almost separate them by decantation rather than forcing them through a filter. They have a very high nickel surface area, so you get a good hydrogen-rich surface. There's no need for any pre-activation, and they're pretty low cost. The problem is, both with the fresh catalyst and the spent catalyst, is this material is highly pyrophoric. So if you've got hydrogen around, if you've got inflammable solvents around, this stuff is tough to handle. It's also very sensitive to exposure to air, oxygen, carbon monoxide, sulfur, low pH, etc. So what are the general guidelines for using a sponge nickel or a rainy nickel? Avoid oxygen exposure, check your feedstock for catalyst poisons. Even the hydrogen, if you've got carbon monoxide in your hydrogen, you're going to form this material called nickel carbonyl. Nickel carbonyl is toxic, and it also leads to deactivation. Avoid low pH so that you don't dissolve off the nickel and get a nice green product at the end of the day, because you've got lots of nickel 2+ in there, and avoid hydrogen starvation. So if we look at a reaction to produce sorbitol, then we're looking for good hydrogen availability. Don't overload the catalyst. Try to get a short reaction time and get to complete conversion. Now, sorbitol is used as a sweetener. It's used in manufacture of toothpaste, and it's made by the straightforward hydrogenation of glucose, usually in an agitated vessel, 30 to 100 bar, run at about 140 degrees. Now, the alternative catalyst to sponge nickel is a 5% ruthenium on carbon. Now, what tends to happen using both these catalysts is you get a very fast reaction at the beginning, and most of the sugar is converted in about a third of the total reaction time if you've got good mixing. You have to have good hydrogen availability, as I've mentioned. The remaining time is used as a kind of polishing step to ensure that the low concentrations of glucose are converted. So here's the reaction. This is what we're trying to avoid, is the formation of this gluconic acid. What we're trying to do is take glucose to sorbitol. Now, gluconic acid is a poison. It also, obviously from its name, it lowers pH. Reduced acid formation, what does it do? It increases your catalyst lifetime. We get reduced elimination, reduced or eliminated dissolution of the catalyst itself, and the ion exchanger that you use at the back end to remove, in this case, nickel ions, is worked a lot less if you have reduced acid formation. So the alternative in manufacture of sorbitol is using ruthenium. Now ruthenium in my time always used to be around about $40 an ounce. I looked the other day, it's now $270 an ounce, or around $8,400 per kilo. Whereas nickel, when I looked the other day, was $15 per kilo. So the relative metal loadings, rhenium nickel is typically around 92% nickel, whereas ruthenium you can use much lower loadings, and you can reuse and regenerate ruthenium very easily. You can run it at much lower temperatures and pressures, and you've got smaller particle size. But one of the downsides of using ruthenium on carbon is that you do need to attend very closely to catalyst separation. There's no decantation, but you get a lot less, almost zero byproduct formation by using ruthenium. Okay, I guess I'm running out of time. So a few more slides. Finding the maximum hydrogenation rate without hydrogen limitation. What we're looking at here is the more catalyst you add doesn't mean that you're going to get a faster reaction rate. What usually happens is when you start to add more catalyst at this stage, it is actually detrimental to the reaction. It leads to more hydrogen starvation and more byproduct formation. So once you reach this stage where there's no more linear relationship between catalyst addition and hydrogen uptake, that's the time to stop adding catalyst, particularly if you're using platinum or rhodium or palladium, which are rather expensive. A little bit about palladium catalysts on a carrier. If we're manufacturing a good fresh palladium catalyst, we'd like to get to between 150 and 230 square meters per gram metal area. Now, there are a number of ways that palladium can deactivate and lose its surface area. One of them is chemical sintering, another is thermal sintering, another is poisoning. But if we just have a look at the effects of sintering, well, if you're oxidizing metallic palladium to ionic palladium, palladium 2+ in this case, you're going to start to lose your valuable precious metal. And dissolution by acid, these are called noble metals, but some are more noble than others. You can lose palladium from the surface of a catalyst, and this is extremely expensive because it tends to leave the reactor. Also, you can get complexation of palladium 2+ species by amines or carbon monoxide, and this can result again in redeposition of the palladium where you don't want it and reducing the surface area of your very expensive catalyst. And here I've included a couple of diagrams to show you what can happen if you get a poor hydrogen mixing inside your reactor. You can start to get oxidation of the palladium to palladium 2+, and that's a real bad scene, because then if there's free acid around, you're going to get this complexation and you're going to lose metal area rather quickly, which I've shown in these slides. Let me just come through to a reaction that Chris will be very familiar with, a very simple reaction on the face of it between nitrobenzene converting to aniline. It looks simple, but look at the side reactions that can take place if you get hydrogen starvation or if you get your reaction conditions wrong. And that's not the only side reactions that can take place. Here is our nitrobenzene again, here is our aniline. We only want to go from there to there. But look at all these side reactions. Some of these things are explosive. If they get out of control, you can get runaway reactions, and there are cases where this has happened on an industrial scale. And that's not the only way that you can get byproducts formed in this reaction either. So in summary, hydrogenation catalyst performance and lifetime is increased by avoiding contact to oxygen and air, good hydrogen availability, don't load more catalyst than you have to, adjust the pH, and check the purity of your feedstocks, hydrogen, and solvents for catalyst poisons. So I'm working for this company called Exeter. This is, I'm doing a bit of consulting for them. This is a bit of blatant advertising at the end. I've put these slides into the back of the presentation for you as well. This shows a little bit about Exeter and where they're located. So if you're interested in converting powders to support materials, then please drop me an email, and my email for this consultancy is there. Thanks very much for your time and attention. It's been a pleasure to present to you.
Thank you very much indeed, Rob. I think in the interests of time, could you have a look at the questions in the chat and answer them?
I can do that. Yeah,
that would be great, because I think we'll need to just move on, if that's all right.
So now I need to stop screen. There we go. I'll stop.
Yeah, brilliant. Thank you.
Okay. I'll have a look at that. Oh, there's lots of chat. There we go.
Yeah. Okay. All right. Thanks very much indeed. And
I'll do that.
Everyone, give you a round of applause. Thank you very much. Thank you.
Thanks.
Okay. The third presentation that we have this afternoon is from Andy Marr. So, Andy, would you like to start sharing your screen?
Certainly.
So Andy is from Queen's University in Belfast, and he's going to talk about biocatalysis and homogeneous catalysis, best kept apart or stronger together. Andy, over to you.
Thank you very much. And thanks to the organisers for giving me the opportunity to talk today. So the scope of this talk, first I'm going to highlight some examples of industrial biocatalysis, and then I'm going to go on to talk about some combined biocatalysis and organometallic catalytic steps. And then I'm going to finish it with something a bit different, some artificial metalloenzymes. So the first process that I want to highlight is actually a whole cell biocatalytic process to produce bulk chemicals. And that, oh, I've gone the wrong way. And that is this process to produce 1,3-propanediol. And this is run by DuPont, Tate and Lyle. And it's run on a large scale. And the idea is to convert sugars to 1,3-propanediol, and the 1,3-propanediol is used for lots of things, including materials and as a solvent. And the catalysis itself is affected by bacterium which has been genetically modified. So this all happens in water, and the bacterium feeds off the sugar, which is derived from corn, and it produces this 1,3-propanediol solution. That then, of course, is quite hard to separate, and there are many steps involved in separating it. There's filtration, ion exchange, flash evaporation, a distillation. But even after all that is affected, you still get a process which beats the original petrochemical process. It's 40% less consuming of energy, and depending how you measure it, there's 20 to 56% reduction in greenhouse gases. My second example is probably better well known, and that's the use of isolated enzymes for pharmaceuticals and active pharmaceutical ingredients. And this example is from work that Queen's University did with Almac, who are based in Northern Ireland. And the original way to do organic transformations using biocatalysts was to find a natural enzyme or a wild type enzyme, isolate it, and then see if it did the organic chemistry that you were interested in. Now that obviously was limited in scope, and now the chemistry and biology have developed to such an extent that you can start with a wild type enzyme, and then you can mutate it into something which works much better than the wild enzyme. So in this example, a wild transaminase was isolated, and that really wasn't active at all for the transformation that they wanted of this ketone, this aromatic ketone, into an amine, and a systematic mutation, bearing in mind the protein structure and bearing in mind the mechanism of the reaction which was desired, allowed over 1,700-fold increase in the rate of the reaction and some really excellent enantioselectivities. So we can truly say that isolated enzyme catalysis for pharma gives high selectivity, high stereoselectivity. It has a low environmental impact. And now we can also say that you can have rational enzyme design. Now, my third and final example of biocatalysis in industry is slightly different, and it's more along the overall topic for the talk. And that is instances in which a biocatalyst is used with a chemocatalyst. So this reaction, dynamic kinetic resolution, which was run commercially by DSM, and there's a nice description of this in this paper mentioned at the bottom by Hans de Vries in Topics of Catalysis. It was operated to produce chiral alcohols, and it's building up on the established reaction of kinetic resolution. So enzymes are wonderful for resolving racemic mixtures. In the example, we have a mixture of two chiral alcohols. If you introduce the right enzyme into the mixture, it will react much faster with one of the enantiomers than the other one. And so you'll get one enantiomer being transformed into the chiral ester in this case, and one being left as the alcohol. And that's easy to separate. But of course, you only get 50% of chiral alcohol, chiral ester. The idea of dynamic kinetic resolution is you can add a racemization catalyst, which is going to interconvert the two enantiomers, and now the enzyme can see all the material. So that's the dynamic part. And this does work with organometallic compounds, and that's what DSM was operating. But you can see from this compound mentioned, which is very good, that the complexity of the organometallic system can be really quite high, and that does hold back these processes. So this particular complex was considered to be too complex to use in the process. And that is something we'll come back to a bit later. So bearing in mind the difficulties of operating a chemocatalyst and a biocatalyst in the same pot, we looked at separate steps. So this is a project that we ran for a number of years in which we were looking at wholesale biocatalysis for the fermentation of biomass, followed by downstream chemocatalysis. So the idea of it was that we know we can take biomass and we can use wholesale biocatalysis in order to produce a chemical. And we know that can be economical because of the 1,3-propanediol process. What we wanted to do was to extract that product rather than completely isolating it and then put it into different chemocatalytic processes. So use it for different. So you could take some of the fermentation broth and use it to make chemical 1, or you could use it to make chemical 2, chemical 3, chemical 4. So these are two separate steps, one of which is wholesale biocatalysis and one of which is chemocatalysis. And the particular problem that we were looking at was the valorization of waste oil. And that was because we were funded in this consortium, which was a European consortium, which was industry-led, to look at the problems of this sort of plant. This is a plant south of Rome in which they take used cooking oil and they turn it into biodiesel. So that's all fine and well, but what you get out the side of it is waste glycerol, and it's impure waste glycerol. In order to improve the overall economics of the process, then we need to use that waste glycerol so that in parallel we can produce fuels and chemicals. So that was what we were given to do, and one of the main driving forces for doing this kind of chemistry is the formation of fatbergs. If we just take our used cooking oil and our used cooking fats and we dump it down the drain, then what we get in the drains, in the sewers, is things like this, the fatbergs. This is a 40-metre long fatberg which developed in the Chelsea sewer, and Thames Water had to clear it. It cost them £400,000 to clear it. So it was a very important thing to use, to reuse your used cooking oil. So let's look at the first step, the wholesale biocatalytic step. And this was done in the Slovak University of Technology by the group of Martin Rebrosch. And they're able to take glycerol and using Clostridium butyricum, and in particular immobilized Clostridium butyricum, they were able to turn it into 1,3-propanediol. So that's the same product as produced in the DuPont processes. And this just shows you that you could repeatedly feed glycerol in and you got the same response of 1,3-propanediol produced. So that's okay. So now we have our aqueous solution full of 1,3-propanediol. Now what we need to do is to separate it out. We need to remove the 1,3-propanediol. And we looked at ion at liquids to do this. And the reason we looked at ion at liquids is because you can get two properties that are very hard to get in any other solvent. And that is firstly hydrophobicity. Well, that's not that unusual in other solvents, but in this case, the hydrophobicity is tunable. So we can build into the functionality the formation of two different phases. And that allows us then to do a cleaner extraction. And the second part is, even though we have hydrophobicity built into our solvent will still have a high affinity for alcohols. And this is the hard one to get alongside hydrophobicity. So the two things together. Okay. So sponsored by Quill in Queens, we looked at a lot of different ion at liquids. So this is some of the data. So each one of these is a different ion at liquid. And we looked at two different classes of hydrophobic ion at liquid. The ones on the left here are the classic hydrophobic ion at liquids, and the anion confers the hydrophobicity in this case, and in particular a fluorinated anion. In this side, these are newer ion at liquids. The hydrophobicity is conferred by a long chain phosphonium cation. And these are quite different. On the left-hand side, we can see here that bistriflamide ones are denser than water. On the right-hand side here, we see this phosphonium one is less dense than water and sits above it. So what we looked at was three different criteria: how well the alcohol was extracted, how specific the ion at liquid was for removing the target diol, and thirdly, and in some ways most importantly, whether the ion at liquid leached into water. Because in the economics of aqueous processes, and in particular wholesale biocatalysis, where you use a lot of water, the water cleanup is absolutely key to the overall economics. So that means if we're dirty in water, we're costing ourselves a lot of money. So we have to try and avoid this water solubility at all costs. So you can see from this diagram that ruled out all the bistriflamide ion at liquids. So we have these ion at liquids to play with because these ones do not dissolve in water, or they have no measurable dissolution in water. Okay, so we ended up recommending this phosphonium sulfonate ion at liquid, and that was because it had good properties: chemical stability, hydrophobicity, non-water solubility, thermostability, and we also saw for our system biocompatibility. What we were able to do was run a fermentation reaction with a layer of this ion at liquid on top, and then look at the product distribution. And we actually found that the production of our product, our desired product 1,3-propanediol, was improved by the presence of the ion at liquid. So that is because there's an extraction happening as you do the reaction, and it can remove poisons from the process. Okay. So one of the first things we did when we started looking at wholesale biocatalysis and homogeneous catalysis was to run the two reactions together. And this was an EPSRC funded study. So what we did was we had a fermentation broth, and then we put an ion liquid layer containing a catalyst with it, and then we showed that we were able to do an N-alkylation. So if you add aniline into the ion liquid, then we find that the catalyst will catalyze an N-alkylation reaction, and we can produce a product. And this does happen, but it's not very fast. And of course, the reason it's not very fast is the fermentation broth is very dilute. So that's really unavoidable if you're going to use the parent fermentation broth. There's some things we can do in order to increase the concentration, but in general, high concentrations of solutes will be detrimental to the whole cell biocatalysts. So we decided that this was not the way to go, that the way to go was the separate steps instead. So let's go back to the separate steps. The second problem was if you have an amine forming in an ionic liquid, it's pretty hard to remove. So we started looking at chemistry to produce something which would be easier to remove. And one thing that we noticed when we did the amination or N-alkylation reactions was that dehydration was happening alongside the amination reaction. And this happened in ionic liquids even when we had water present. So we looked at, could we do the dehydration as the main reaction? So we'd leave the amine out of the reaction. And in fact, these kinds of catalysts and under basic conditions will convert 1,3-propanediol into aldehydes. And they do that first by dehydrogenating. So we remove hydrogen, we produce an aldol. The aldol under base will spontaneously dehydrate, and then it gets rehydrogenated to propanol. So this is the next reaction that we looked at. And the good thing about this reaction is the propanol, because we've removed oxygen from it, is more volatile than the 1,3-propanediol. So what that means is we can run the reaction under a low, mild vacuum, and this is very achievable industrially. So, and then we had the ionic liquid here with the product and the base. We run the reaction and we can remove the products as they're formed. And if you remove the products as they're formed, not only, of course, does it improve separation, but it also improves the selectivity and the rate of formation of the product. So that was the right way to run it. And we found that we were able to run it repeatedly. So we could run the reaction again and again. We're using an iridium catalyst because we found them to be very stable under these conditions. Now, the catalyst was stable, and we could produce after the first run a very consistent product distribution. But if you see this in red here, the base was unstable. So we tried a few bases in this, all of which were unstable for the recycling. So these recycles are all done by adding additional base. So that started a parallel study on finding heterogeneous bases that were stable. And we managed to solve this problem with a basic ionic liquid gel. Now, I'm not going to talk about ionic liquid gels because I don't have time, but we have had a whole series of different experiments on these and shown acidic ionic liquid gels as well. This silica ionic liquid gel, it's basically just silica with a basic ionic liquid entrapped inside. And what we found with this was that if we use that instead of the soluble base or semi-soluble base, and we put the catalyst in, then we could run the reaction again and again with no decomposition of the base. The ionic liquid inside that is a phosphonium hydroxide in this case. Anybody interested in ionic liquid gels? We have written a review on it. Patricia is the real expert on this. It's in Green Chemistry. It was in 2016, page 105. Okay, so propanol is not the most exciting product in the world, so we were interested, could we diversify the products that could be produced using this chemistry? And we found that we could. We could produce 2-methyl-2-pentanal by changing the conditions of the reaction, and that was a very reliable reaction as well. So we've managed to show what we wanted to show, and that was that we could use whole cell biocatalysis on different biomass to produce the same renewable platform chemical, that we could extract these platforms with ionic liquids, and then we could feed them into different chemical reactions. And I showed you the secondary means propanal and the C6 aldehydes, but we also had some reactions on nitrogen heterocycles as well. Okay, I would like to go back briefly to the idea of putting a chemocatalyst and an enzyme into the same pot. One of the reasons why there were very few catalysts known for this reaction, for the dynamic kinetic resolution reaction, was that the hydrogen transfer catalysts used required a base. And the base, when used alongside the enzyme, tended to decompose that enzyme or affect its reactivity. So a few years ago, we developed some hydrogen transfer catalysts that didn't require base and could be used alongside the enzymes very efficiently. And that's these catalysts, and you see we've been using these types of catalysts for the other transformations as well. So CP star, rhodium and iridium, and heterocyclic carbene catalysts. The reason I mention this again is because of what we discovered when we were studying that. What we found was that the dynamic kinetic resolution performance was very enzyme dependent. It also varied as you had different types of enzyme immobilization. So yields would vary from batch to batch of the enzyme. We believe that this is because of an enzyme catalyst interaction. So I've got a little cartoon here. Here's our nice enzyme. It's all happy. It's sitting in solution. And then you dissolve in your organometallic complex. That organometallic complex, by its very nature, has to be labile to be a catalyst. And it can find groups on the polypeptide that are exposed, and it can react with them, and it can become poisoned. This is obviously not to scale. So that leads the question, well, if there's going to be a protein organometallic interaction, can we use that interaction to our advantage? And that's where we come into the idea of artificial metalloenzymes. So in artificial metalloenzymes, we encourage an interaction between an organometallic complex and a protein. And then we use that protein to tune the chemistry. So the example that I'm going to use in this talk was first developed in the labs of Professor Paul Kammer. And what they did was they started with a protein, and then the protein cysteine residues were reacted with an organic linker, which was then attached to some sort of ligand. And so you get to control where the linker goes because you can control the amino acid sequence and where the cysteines are present in the polypeptide, the primary structure. This modular design then allows you to change what proteins you're using and to change what ligands you're using. And a lot of that was done. And the example that I want to talk about just briefly is an artificial hydroformylase. So I notice Amanda's in the audience. Amanda is the person that published this with Paul. And this system was particularly good for the hydroformylation of longer alkenes and producing a good linear aldehyde ratio. And the great thing about this system is the amount of work each individual metal does. So you get hundreds of thousands of increase in activity per rhodium center. The system that they produced, there's good evidence that it only contained one phosphine per rhodium, and it had a really remarkable selectivity, considering that it only had one rhodium per phosphine. So the protein was really influencing the reactivity. So then once this was discovered, this artificial hydroformylase, we came into it, funded by the Catalysis Hub, in order to work with them and to try and tune these systems. So XSAFs had revealed that there was a role in methionine. in the rhodium binding of these catalysts. So what we did was we looked at systematic mutations at the methionines. So there are 4 methionines in the 2 most active catalysts. We varied just 1 methionine at a time, and then we measured the hydroformylation, and Tanvir Imam is the postdoc involved in this research. To our surprise, we found that all of the mutants exhibited higher activity than the parent proteins. This is not something we can easily explain at the moment, but what it tells us is that this systematic improvement using the polypeptide is very possible for artificial metalloenzymes in the same way as it is for an enzymes, and they have an enzyme-like complexity. So that's where I'd like to leave it. And in conclusion, it's hard to find suitable conditions under which to combine conventional biocatalysts and homogeneous catalysts in one pot, but combined consecutive biocatalytic and chemocatalytic steps will enable a large variety of chemicals to be prepared from simple biorenewable feeds. And combining organometallic complexes and proteins as artificial metalloenzymes produces unique catalysts that operate in water and can be tuned by mutation. And that's it.
Thank you very much, Andy. Okay, we have a few minutes for questions. First is from Stephen Wallace. Nice talk, Andy. Andrew, I didn't hear what fold increase in product formation from your clostridial cells you got as a result of your ionic liquids, and how you confirm that the ionic liquids were biocompatible to your cells.
This is all published. It's a minor improvement. I would say that the main reason for the cell survival is more the low water solubility. I don't think that it's particularly anything molecularly clever about the system. The system was mainly chosen for good phase behavior rather than this biocompatibility. It was a surprise. It's a sort of an addendum to the study.
Okay, thank you. There are no further questions. I'm going to encourage people, given the time, I'm going to encourage people to type more questions into the chat as we go along. And then if Andy, if they come through, if you could answer those, that would be helpful. But hopefully we'll get a bit of time right at the very end, but it depends on how long Catherine talks for. So thank you very much again. That was excellent. Thank you.